In this chapter, we will look at vortices and vortex shedding, buffeting, and symmetry in aero, rim, and tire combinations. When you want smooth riding ahead, but get vortex buildup instead, you need some deterrence to unstable currents when it's time for the vortex to shed. This photo here shows regions of unstable air being shed as vortices off the wingtips of this airplane. All airplanes do it, both big and small. And so do bicycle wheels made with deep section carbon rims, which we're now going to look at. In these computer drawings here, we're looking at some images of a moving wheel. We know that the moving wheel has both translational and rotational kinetic energy, and those combined motions create air molecules that briefly accumulate on rim surfaces in recirculating currents. They're on both sides of the wheel, and these are regions of unstable air that are shed periodically as vortices. I've developed some graphics to help us understand this. Here we're looking at a top view of a front wheel, and the wheel is rotating forward in the direction shown. We see some molecule accumulation on the rim and circulating air currents, and that gives us equal sideward pressures. You can use either sideward pressures, you can call that normal pressures, or orthogonal pressures. They all mean the same thing. We want to see what happens now when the vortex sheds on one side of the wheel, but before it's had an opportunity to build up again. If the vortex sheds on the right, then we suddenly have unequal pressures and the wheel wants to turn to the right. If I have a little bit of side wind, as shown here by the red arrow, then when that vortex sheds, I also have a partial vacuum created on the right-hand side of the wheel. In a similar way, somewhat unpredictably, the vortex will shed from the left, and then I have unequal pressures once again, and the wheel wants to turn to the left. This periodic loading and shedding of vortices creates buffeting. As I rapidly transition from this to this, to this, to this, to this, to this, to this. This is not because the wheels are out of true, and it's not because the frame is misaligned. In a time trial or triathlon bike, bikes like this are not easily maneuverable in the first place because you have a lot of the rider's weight over the front wheel, and we don't want the rider to have to expend a lot of energy in controlling the bike. So our goal in designing the wheels is to have frequent shedding of small vortex buildup to minimize the amount of buffeting. We're going to get more buffeting from this picture. Than from this picture. The picture on the right with frequent but small vortex shedding is going to create less buffeting and be easier for my rider to deal with than the more pronounced effect on the left. Less buffeting gives us more stability and a faster rider. Subtle changes in the design of the rim can affect this concept of vortex shedding, and there's a lot of engineering and testing that goes into designing rims to minimize this. Next, we're going to look at some combinations of aerodynamic rims and tires and see what they have in common to reduce aerodynamic drag. Using ZIP as a case study, we can look at the evolution of carbon rim shapes, and over on the left is the traditional V shape, and then that was turned into the 404 clincher with a hybrid toroidal profile. And over on the right, we have then two newer rims, the 404 carbon clincher with a firecrest profile, and next to it, the same rim in a tubular. Under that, I'm going to put a tire on each of those rims. Our bike is rolling to the right, and this is the original zip rim. The wind hits the front tire, has to go around the rim, and in the back, around the rim, and then around the tire. The wheels face the same situation with the toroidal, and then these last two, which are Firecrest rims. And Zip has found from testing that there is less total drag for the wheel as a whole with the Firecrest, improved behavior in crosswinds, less steering correction required, and aerodynamics advantage maintained at higher yaw angles. This is the Bontrager Aeolus D3 wheel, dual directional design, and its graphic might look something like this. And we're getting similar outstanding R&D results from this wheel. Some of its features: low weight, very good climbing, optimal handling with yaw angles, available in a tubular or clincher. Here we see 4 beautiful wheels by MV Composites. The SES 3.4, 4.5, 6.7, and 8.9. In each case, there is a rear wheel that matches the front but is a little bit deeper. SES stands for Smart NV System, and Smart comes from a British engineer named Simon Smart. And here are 4 beautiful mountain bike wheels. The higher number over to the right means that it's intended mainly for downhill racing, whereas the one on the left, 50% downhill, 50% regular mountain bike riding. This is another rim that I like very much. It's carbon rim designed by Boyd Johnson. Boyd formed his own company, Boyd Cycling. The web address is at the bottom. And we see the same kind of an aerodynamic advantage with this tire rim combination as we've seen with the other examples. The wheel is rotating and traveling to the right. This is the relative wind. The wind has to then get around the tire and the rim in the front of the wheel, and in the back around the rim and then around the tire. All of this has to be done with a minimum of drag. Boyd designed his rim to work well at typical yaw angles. Another company I want to mention briefly is Knox Composites in Knoxville, Tennessee. I note some really neat graphics. If I looked at the rim from these vantage points, I would see NOX. Here we see the dimensions of the rim and directions on which way to lace it because of its offset pattern. Here I have oriented the rim correctly for both the rear and the front wheel, and the rim is centered over the geometric center of the hub. But my spokes are going to connect to the rim as shown here. With my rear wheel, the connection point on the rim is moved slightly to the left, and that opens up the angles theta and makes my spoke tension more equal on both sides, and more importantly will improve the lateral stability of the wheel. The analogous picture for the front wheel shows that angle phi has increased. So in both cases, my angle to the flange on the high tension side of the wheel has gotten larger. Let's go back to this graphic of a wheel made with a Firecrest rim, and I'll give you what I think is the takeaway from these examples we've been looking at. I made here a graphic which is a nice aero rim. Now we have a tire on the wheel. I think that what we're seeing is this, that when we have a good combination of reduction of drag of the leading edge and the trailing edge of the rim tire combination, then we find that we have a plane of symmetry where half of the wheel tire combination is a mirror image of the other half. In some very high-end wheels, maybe for a time trial or a triathlon, you'll see even a little strip put in here where the tire meets the rim. to fill in even that little tiny gap. There are differing viewpoints by industry experts, and people can look at the same facts and the same wind tunnel tests and so on and come to different conclusions. For example, here's a ZIP 404 Firecrest rim, unquestionably a great rim, and let's assume that my air coming toward the wheel from the right, opposing the rider, is in a perfect laminar flow going around the rim and exiting off the back also in a perfect laminar flow. But I quickly run into turbulence that's going to be caused by the whirling spokes, the hub, and the fork. So I have quite a lot of turbulence when the air meets the back half of the wheel. And that turbulent air prevents me from getting a nice streamlined flow around the back half of the wheel that I assume I may have gotten from the front. With that in mind, let's take a look at a wheel made with a Reynolds Aero 72mm rim. This is a graphic of a symmetrical airfoil, and this is a graphic of a Reynolds Aero 72mm rim. If I make a copy of that rim section and turn it around, I have this picture, so it's clear that the similarity of those two pictures makes the aerodynamic profile of the Reynolds Aero rim similar to the airfoil. Both of these shapes will give me the same low drag coefficient, and I should have air efficiently passing over and under the surfaces and staying attached quite effectively. Here is my wheel with tires installed and moving and spinning toward the right. The air comes up to the tire, passes around the tire. The aerodynamic shape of the rim ensures that the air will stay attached. Because the air stays attached, we get a little bit of a bonus, and we'll look inside this box here and expand that. The streamlined air passing around the rim creates a normal pressure on the surface of the rim. That pressure can be resolved into vertical and horizontal components. And this little bit of return energy here actually helps propel the rim forward. So Reynolds has made a pretty compelling argument for the efficiency of this rim. This disappointing picture of drag reduction in a front wheel, where you get only a benefit on the front half of the wheel and not on the rear because of turbulence caused by the fork and the spokes, and the same thing happening with the rear wheel, is only going to look like that if the air is coming directly straight from the front, and normally that won't be the case. Normally there's going to be at least some amount of yaw angle, and you have in that case rather pristine air making contact with both sides of both wheels.